When it was first discovered that in certain terrestrial rocks, the measurement of the Earth's dipole suggested that what we refer to as the North Pole was at certain points in the Earth's history located over what is now the South Pole. It was thought to simply be an individual event, perhaps lightning struck, the rock bed of interest. But data from all over the world not only suggested that the pole reversed, but at the same time. And so rocks of similar age on different continents were providing evidence of the same magnetic reversals. Even stronger results came when the dipoles from the rocks of the ocean crust at the bottom of the ocean were measured using magnetometers. There are different types of magnetometers. Some could be used, say, with a terrestrial rock to measure where the direction of north was pointing. A magnetometer that is dragged behind a boat measures the direction of the Earth's dipole differently. Any magnetometer, even a compass, is responding not only to the dipole from the Earth's magnetic field, which would point north, but then also the dipole from any magnetic field in rocks nearby. And so, as one drags a magnetometer behind a boat, if the rocks beneath have a dipole pointing to the same north as the Earth's dipole at that moment, then they would add together and produce a stronger dipole for magnetic north than would be measured simply by the Earth's magnetic field alone. This is referred to as a positive anomaly. If, however, the magnetometer is passing over rocks where the dipole from their magnetic fields is pointing in the opposite direction, that would subtract from the strength of the dipole from the Earth's magnetic field, leading to a negative anomaly. And so then one could drag a magnetometer behind a boat and thus in pass after pass after pass measure the dipoles from the magnetic rocks of the ocean floor as either being in the same direction as that of the Earth or in the opposite direction. A fascinating observation followed. The exact same pattern of positive and negative anomalies was observed on either side of a mid-ocean ridge, suggesting that whatever caused this change to occur, say, on the east side of a ridge, in the case of, say, the mid-Atlantic ridge, the exact same pattern was observed on the west side. This pattern of positive and negative anomalies not only compared on either side of a central mid-ocean ridge, it also compared to what was being observed in the terrestrial rocks. The terrestrial rocks and later the ocean rocks could be dated to show that these reversals and periods of normal Earth's dipole correlated to different points in time. That the planet for a while had a normal dipole where magnetic north is pointing to the present north, what would be called a chron, a normal chron. And then there were periods where there was a reversed chron where the magnetic north was pointing south. In the middle of these large crons, there were sometimes temporary subcrons where for a short period of time the Earth's magnetic poles would reverse. So the rocks on land and on the bottom of the ocean were recording changes in the magnetic field over time that occurred all over Earth. This indicated that these mid-ocean ridges were creating new oceanic crust. Not only was this oceanic crust recording the magnetic north at the time that it was formed, the great quantity of oceanic crust coming from these mid-oceanic ridges then suggested that the bottom of the ocean is not really fixed, it is dynamic. And thus, as more and more oceanic crust is created, that this would then be pushing continents apart. So for example, when Pangaea, the supercontinent, broke up at the early Jurassic, it would have been the new magma forming new ocean crust at the bottom of the ocean along the mid-Atlantic ridge, which would have been a driving force.